Hello, and welcome to Ask the Expert Live. I'm your host, Randy Stott, and I'm the managing editor of Gear Technology and Power Transmission Engineering magazines. Thanks for joining us today. Our topic today is lubrication, and I've assembled a panel of experts here to answer your questions, as well as questions from other readers who've submitted in advance. The way this works is, if you have a question, raise your hand and ask it, and I will make sure that we get an answer from these guys here. And with that being said, I would like to give them each an opportunity to introduce themselves. So we'll start with you, Paul.
Thank you, Randy. My name is Paul Conley. I'm Chief Technologist for SKF. I've worked for SKF for 23 years. I work out of the St. Louis, Missouri facility, and a lot of our experiences in Type 2 open gearing and lubrication of gearing. So I'm more apt to answering questions on means of lubrication of gears, depending on what type of lubricant is being applied.
Paul?
My name is Hamid. I work for Lubriplate Lubricants. We make mostly industrial lubricants, including gear, hydraulics, and compressors. I have been working for this company for the last 10 years. I'm a chemist by profession, also the technical director for the company.
Thank you, Sid.
Yeah, my name is Tobie. I'm working at the Gear Research Center FZG in Munich, Germany. I'm there working as a department leader, and I'm involved a lot in testing of gear lubricants, the FZG tests, and also research work on the influences of lubricant and lubrication on the gear performance.
Very good. Thank you, guys. I'm going to start right in with one of the questions from our readers. And it is, for a fixed viscosity grade, which lubricant base stock results in the highest gearbox efficiency?
I'll try to respond to that. Gearbox efficiencies are related to the molecule, the kind of molecule you use. When you compare the mineral oil with a PAO and a polyethylene glycol PEG-based product, and also ester-based products, you will see that the coefficient of frictional properties of these base stock, and compare it with them. In our study that we have done, we see that polyethylene glycol or PEG-based product provide the better gear efficiency in the systems that we have tested. Also, I think that when you select a polyethylene glycol, it reduces the temperature. The heat is reduced from, I would say, about 10 to 15 or 20 degrees F temperature, and that provides the efficiency as well.
Okay. Anybody else like to add?
I can absolutely agree to this statement. So the polyglycols typically have a much better coefficient of friction, and this is the most important influence on especially on the load dependent losses, and gives you a high efficiency. So the difference between PAO and mineral oil is maybe a smaller one, but especially polyglycols have a better coefficient of friction.
What about the same question with regards to micropitting resistance?
You want me to attempt that?
Go ahead, Thomas.
Maybe I can try to answer that. I think it is important to notice at first that micropitting can be observed in the lubricant regime of mixed lubrication. If you have a full separating film, then you will not observe micropitting. So in the mixed or boundary lubrication, micropitting may occur. And I think from our researchers, in my opinion, the most important factor on the micropitting performance is not the base stock, it's the additive package in the regime of mixed lubrication. Mm-hmm. But of course, there's also an influence from the base stock. And then it's a similar effect. You have a lower coefficient of friction for polyglycol. This reduces the additional stresses on the surface and may also result in a higher film thickness. So in tendency, synthetics have a better micro-pitting performance. But again, the additive package is a very strong influence in addition to that.
Mm-hmm. Is that same question related to EHL film thickness?
I think EHL film thickness is also influenced strongly by our base stock, but there are several parameters that you have. Synthetics typically have a much higher viscosity index than the mineral oil, for example. So especially at the operating temperature, if you have the same nominal viscosity, and then you have a higher operating temperature, then you have a higher viscosity for the synthetic and a higher film thickness.
Okay, very good. Next question I have is, how does a type of gear lubricant affect how the lubricant would be applied in an automatic lubricant system? Maybe Paul can start.
Okay. Well, the type of, has to first depend on its sprayability and pumpability, obviously. Real high tackifier greases are much more difficult to apply. However, greases that are more pumpable with solvent added are sprayable. So there's an air spray that can be applied, and the systems are set up to where you're applying the spray directed, on the load zone of the bearing. And lubricants that have a high percentage of additives of AP additives, those are can be used with spraying also within limits of the pumpability. So the additives don't necessarily detract from pumpability unless it has to do with its thickness and tackifying. But I would say that the most efficient form of applying lubricant is through idle gears. That a grease is pumped to an idle gear, and the lubricant is dispensed right on the pitch line of the gear in small amounts. So it's very efficient, and it could be a very thick grease, or it could be a thin grease. So, depending on the pumpability, primarily dictates how, if you're going to use a spray, air spray, an airless spray. What the airless sprays are used on real synthetic greases, where there's synthetic hydrocarbons, real high viscosity, tacky, where it's heated up and then sprayed in the load zone of the bearing, because you can't use air to distribute the grease adequately to the gear. So, so that would be it.
Okay.
I don't want to ramble too much, but.
Would you like to add?
Can I add something to it? Yeah, pumpability is affected by the type of base stock and the gelling agent that you use. Some are better than the others. We have found in our system that the calcium sulfonate greases, if you just use mineral oil in it, they are harder to pump compared to the other greases. But if you use a synthetic oil, at different temperatures, they vary in pumpability results. For example, if you use a PAO in a grease, at lower temperature, it's going to pump better, of course, because of the low temperature properties of the base stock. And also, it is affected by the additives, like Paul said, and the thickeners that you use. The type of thickener we have seen, some of the aluminum and calcium-based products, they pump better compared to the calcium sulfonate greases.
Okay, thank you. I'd like to follow that up with another related question, and that is, what are the different types of automatic systems for lubricating gear drives?
I would say, the types are an air spray system where grease is pumped to a valve that goes to a nozzle. And the nozzle has a port for air and a nozzle has a port for the grease. So when it's time to lubricate, you turn on the air, and then you turn on the pump, and it will dispense grease to the valve, to the nozzle, and it will force the grease into the load zone of the bearing. So an air spray is one. The second one is airless spray, and that's for thick lubricants, poor pumpability, or or the environment is cold and the lubricant is extra thick, is that grease is pumped into a valve that is heated up, and that valve has pressure behind it of about 2,000 psi or 150 bar minimum, and it is spray directed into the load zone of the gear. That spray, the grease is heated to maybe, I would say, 180 degrees Fahrenheit, just below a damaging of any temperature that's too excessive for the lubricant. And then, but as it comes out of the nozzle, there's the diffusion, there's the cooling back down, so that the viscosity is back to where it can maintain a film thickness to prevent metal-to-metal contact to the gear. In that system, you have to be careful that the lubricant isn't spraying too much in the root zone, because we've seen that, when the gears mesh, they force each other out, and you cause problems with shock loading of the bearings that support the gears. And so the next type, which I believe is the most efficient, is an idle gear, and it has the same gear module as the gear that's lubricating, and it rotates freely from the power of the gear. Grease is moved into that idle gear, pumped in, and it's dispensed to the gear teeth of the lubricating gear, of the idle gear, and it dispenses the lubricant right on the pitch line precisely, so that the grease is then put on the pitch line, and it's right in the contact area of the teeth. And if it has a minimum amount of tackiness, you can use very, very low amount of consumption and maintain a very, very good film thickness. So that type of system, which we call a gear idler system, that grease is pumped to that, fans out to the gear, and working gears pitch line.
Okay. Thank you. Very good. I'd like to remind the audience, if you have questions, just raise your hand and I'll get you a microphone. Is there an official or even industry recognized definition of what is a synthetic lubricant?
I'll try to attempt that. Synthetic products, if they are made from components, basic molecules, and reacted, those products can be called synthetic. There is a definition that Bureau of Better Business has defined Group 3 oil to be defined as the synthetic as well, for isomerization that they did to that molecule. And because of that, there is a synthetic component to it, that it's not just the hydrogenation part of it, where these days all of the mineral oils are being hydrogenated, meaning hydrogen is added to end cap and to make it more thermally stable. But they have done more than that. So based on that basis, some of the products that use the Group 3 oils, they are considered synthetics. But generally speaking, if you start with the basic components, they are derived, mostly they are derived from petroleum fractions, but they are chemicals, and these basic molecules, when they are converted from a low molecular weight to a higher molecular weight, that becomes the synthetic products.
Thomas, is there a difference of opinion from the European perspective?
I think PAO and polyglycol definitely are synthetics, also the esters. Group 1, definitely non-synthetic. Group 2, and Group 3, I'm not sure if in the European community they consider Group 3 as a synthetic, as a full synthetic. But this is maybe some point of discussion or not clearly defined at the moment.
Do you think that there is some marketing element to calling the lubrications synthetic, or a pressure to call them synthetic when maybe they're not fully?
Definitely.
That exists. Yeah.
So how does the consumer really differentiate, I guess, is the real meat of that question.
It's hard to, in marketing, advertising and all of that, it's a different way of defining it versus in the actual chemistry part of it. I do understand the part that the Group 3, why the Group 3 are being called synthetic. because they have done more than just hydrogenation. They have done isomerization part of it. That changes the molecule.
Okay, thank you. This one's a little more technical here. Two methods exist for assessing scuffing risk: Bloch's flash temperature and the integral temperature method. Which is more reliable and why? Thomas?
Yeah. Both methods are available for a long time. And there's no clear answer what is the better one or what is more reliable. I think both methods assume that there is a maximum temperature. If you reach the temperature into contact or exceed it, then you will have scuffing. The flash temperature assumes that the local contact temperature, which is only in a very limited time available on the surface of the gear flanks, and looks localized in each contact point and looks for the maximum. So the principle is, I think, the right thing, the right assumption, but it's sometimes very difficult to make the calculation of all the local values. So you need some understanding, some very good understanding, a calculation method. For example, the local coefficient of friction or the local load, including dynamical effects. And this value may be influenced by some single temperature peaks very strongly. And if you have some flank modifications or some extreme gear design, then you may calculate unrealistic values. And this gives you a wrong impression regarding the scuffing. The integral temperature takes an average along the line of action and is not so sensitive to that. So I think if you consider that maybe in the future you get a better understanding of all the local values, I can imagine that for the future the flash temperature method will be used more and more. What I see at the moment is that many companies are using both methods in parallel and control the values to fulfill the requirements on this. It's really depending on the experience and the knowledge that you have.
Okay. Very good. What is the difference between false Brinelling and fretting corrosion? And how can false Brinelling and fretting corrosion be prevented?
Should I try again? Yeah.
If you,
Yeah, go ahead.
if you think you've got a good, go for it.
Yeah. I think both can be included in the expression of fretting. And fretting covers two mechanisms. Fretting occurs if you have a gear pair that is not rotating, but have some small oscillating movement. And due to not rotating, but the sliding, you have only a very limited amount of lubricant in the contact. And false Brinelling is the first mechanism that is some kind of incubation period, where the gear flanks, they have a very small amount of lubricant, but it's boundary lubrication. And in consequence, you will see some very mild adhesive wear that is typically limited on the natural oxide layer that covers the surface. And once there's the time that all the lubricant disappeared in the contact, and then you change from the boundary lubrication to the unlubricated contact. And then the oxide layer is broken down, and then you have strong adhesive wear. So one follows the other, and both can be designed as fretting, whereas on gears, false Brinelling typically is not a severe damage on this. You can see it clearly on the surface, but it's not a severe damage. Once you have reached the unlubricated condition and you have fretting corrosion, then you really have a strong adhesive wear, and this is then a damage on the gear.
Anybody like to add anything?
But I mean, wooden true Brinelling is just the damage due to the stresses that are higher than the value of the metal on the gear, where the fretting and the false Brinelling is kind of how you described it, just microscopic
Yes.
motions
Yes.
that really can deteriorate the gear.
Yeah.
But true Brinelling is more when the contact stress just exceeds that of the metal's yield, tensile ultimate strength.
Yeah.
Very good. How does the type of open gear lubricant influence the frequency of relubrication?
Yeah, this is something that there's not a precise science. So, when you install a lubrication system into a gearing, usually we have temperature measurements that are shot on the gear teeth, and you look at the gradient change in the lubricant. So greases that have good tackifiers, we usually find out that they can be maintain a good film depending on the speed, of course. 15 minutes or so. I'm talking about in applications of large open gearing. That's what I can speak to mostly in my experience. Is 15 or so minutes where you have reasonable amount of tackifier attached to the grease, where you have maybe solid additives, metal additives, in the paste. That can be extended, but when you have non-tackifiers or more of oils, you lubricate more frequently. But you have to be careful not to lubricate too much and fill the root zone of the bearing, because it causes separation forces, and that's very undesirable. So, we usually, installing a system, you have usually a heat gun, and you can look and see where there's a change. You can definitely see where the temperature is in a good film regime is pretty reasonable, and you can see it peak up, and that's kind of the time when the installers do this. They're instructed to note that time the temperature increases and set the frequency lubrication accordingly.
Yeah, I'll just add that to it. Open gear greases, mostly they are loaded with a lot of solids, carbon black and moly and all of those kind of compounds. It's hard to distinguish between just by looking at it, saying it's still going to work or not, when to change it. I think one of the thing I call greases as sponge that absorb all the oil and additives that actually lubricate. Grease mostly act as just a reservoir for the oils to be released under pressure and temperature conditions. When these oils are released, they actually lubricate bearings of gears. So one of the things that we could test in the laboratory, there are two ways to test it. One is to see how much acid has formed during that process. So if your acid number is high, for example, 4 or 5 acid number compared to the original product, you can tell that there's a lot of oxidation has taken place. And you have to set your own limit as to when you want to change that oil. In the laboratory, we have done it between 3 and 4 for some greases, depending on what the base stock and the structure is. But I think it's laboratory testing is critical to prolong the lubrication of any oil or greases.
Okay, thank you. I have a reader who asks, for some of our gear drives, the OEM is calling for a compounded oil. What does that mean?
Should I respond to that?
Sure.
Compounded oil means that it has additives in it. It has the proper additives for the application. And non-compounded oils have just the base stock, whether it's mineral oil or an ag, or it's non-compounded without any additives. But when you add the proper additives for the application, if it's a gear oil, you're going to add the anti-wear EP additives in it. Mostly these products are sulfur phosphorus kind of chemistries that you use. And then you have to use, for rust protection, you have to use copper deactivator, antioxidants. You have to make sure the polymeric, if it's for low temperature application, you need to use some polymer if it's a mineral oil based product, or just a synthetic product that can go to the low temperature and measure that.
I could just say that, the compounded products are pretty necessary there's a lot of sliding friction and worm gears, so the additives in there are to reduce the wear and the sliding friction, which is more difficult than in a gear type contact. Where there's not much sliding, it's more rolling, and with some sliding. Where in a worm gear you get a lot of sliding, and the compounded oils are important for that.
Yeah, but I think for most gear applications, you need some additives.
Oh yeah, you need additives. Yeah,
you have always some sliding.
But compounded is kind of a specific additive.
Yes, exactly.
Yeah.
But I think without any additives, it's very difficult to operate, to transmit power in the gear contact.
That's true. There's always additives.
Can I add something to that
Yes, please.
effect? The additives for the gear oil, for anything loaded, what happens is that if it's a additive that forms a tenacious metallic compound on the surface of the metal, and that metal actually is the one that carries the weight. It helps in carrying the larger weight if you have found that metal composite of your additives and the metals that are involved to carry that larger or shock load of the gears.
Thank you very much. This might be from the same reader, but the question is, my lubricant supplier says that if we switch to a synthetic, we can expect to see a 10% reduction in energy consumption. Is this true?
Go ahead.
I'm not sure about the number. 10% is one value, and I think it's strongly dependent from kind of gearbox and the operating conditions that you have, and so on. But definitely, as we have discussed at the beginning, synthetic fluids have a better coefficient of friction, and this will give you a benefit in the efficiency. How much the benefit is, depending on speed, temperature, viscosity grade, how many gear stages you have in the gearbox, and so on and so on. It's not an unrealistic number, but can be very depending on the application.
Well, I would say generally synthetic lubricants do have an advantage over energy consumption versus mineral oil because of the properties it has. It has a better VI, viscosity index. It runs better at various temperature of the application from start up to the higher temperature. So it has to save energy on the kilowatts versus the mineral oil that has waxes and other products in it that do not allow that lubricant to have the similar viscosity at the same temperatures or at the maximum temperature that is the operating temperature at various stages of the application.
Very good, thank you. We touched on this a moment ago, but this next question is, what are the special requirements of lubricating a worm gear drive?
Coming up in just a few minutes, please join us in the Solution Center for a presentation called High Performance Grinding Solutions for Gears by St. Tobie. Please join us for a Solution Center presentation starting in just a few minutes. Also, in the Emerging Technology Pavilion, booth 4239, please join at 11 o'clock for a presentation by Machine Metrics. That's in the Emerging Technology Pavilion, booth 4239.
So what are the special requirements of lubricating a worm gear drive?
As already mentioned, you have crossed axles in worm gear drives. This results in a high amount of sliding. This is correlated to a strong increase of the temperature, and this is certainly one reason why you have special requirements, and very often you will find synthetics in the application for worm drives. And there may be also a second effect, because the direction of the rolling is not perpendicular to the contact line, and this is difficult to build up, or more difficult to build up a good film thickness in the contact. And then of course you have some special materials also need to be considered. It's not the same as for other type of gearing. So there are maybe some special requirements on the chemical interactions.
And are there certain additives or compounds that are especially used for that?
Yes, we think that the warm gears lose most of the energies compared to a lot of other applications in the other type of gears. So you need to formulate a product not only from a base stock point of view to select the right base stock, but the additives are very critical. Because there's going to be energy loss in it, so you need to minimize that. And some of the minimization can be done by adding the proper amount and the kind of gear additive. Mostly in this case is wear and EP additive. If the extreme pressure additives are going to last for the time of the application, during the time this gear oil is used, that is what is needed, and the longevity of the additives are critical because in the midlife, I call it midlife crisis, when some additives lose the additives are depleted and they are gone, and now they have to rely on the base stock itself. That is a midlife crisis for the oil, and that is a critical part that the formulators like myself care about it. They want to make sure that the additive that they're using in any base stock, whether it's synthetic or mineral oil, is going to last throughout the life cycle of the gear oil.
Very good. How does automatic lubrication benefit the life of heavily stressed gears?
Well, the main thing with automated lubrication is applying grease frequently, usually less amounts and frequently. So with that type of mentality and type of application, where you can put small amounts in, a little bit more frequency into the load zone of the gear, you can ensure there's a sufficient boundary layer or elastomodynamic lubrication at the contact points, and then you can resist pitting and scuffing and things longer. So it's a philosophy of applying the lubricant in such a way that you can ensure maintaining a good film thickness and thus reduce wear. And the life of the gear goes up.
Very good. When should I use a different oil than what is recommended by the OEM?
I would say if you have gear failure,
Yeah, if you have problems in the field, then you should think about to change the lubricant.
Is there any guidelines or advice to give people in those cases?
I think it's very specific depending on the application that you have. There are so many gearboxes out in the field, smaller ones, large ones, high speed, low speed. So there's no general recommendation.
Is there a case before failure when you would consider that at the design stage or the early implementation?
I think if a preventive maintenance program is involved, predictive maintenance where you're looking at temperatures of the bearing or the temperatures of the gear and you see higher temperatures, there's something going on, and to bring, a lubricant company in to analyze it, or the gear manufacturer to look at the application again and see if there isn't something better that can be done.
Yeah. I think that's very important. If you make a new design, then you need on one table the different people from the lubricant supplier and the gearbox manufacturer, so that the lubricant supplier understands what are the requirements, what are the conditions, and then they should be able to give you a good recommendation. If they have no idea what is the real application and the requirements, then you can use a standard gear oil, but this may not be the best choice in such a case. So it's very important to talk to each other.
Is it common to run it and then test the oil, send it to a lab?
I was going to say the maintenance of lubricant after sale is very critical. You have to monitor the oil in that condition. And again, oil in any machinery is like a blood in your human body. And when you get sick, your doctor will test your blood first. So that's how the oil is. If there is anything going on with the mechanically, with the higher load or shocks or contamination in your gearbox, the oil analysis is going to tell you that. The oil analysis normally is done like a FTIR, a fingerprint of the oil. It is tested for acid number. It is tested for any debris or any kind of wear metals that are coming out of it. All of this is predicted prior to the actual failure that when it happened. So maintaining your lubricant throughout the life cycle of any gear oil is very important.
Very good.
But I would just like to reemphasize that, you know, the company should have a good preventative and predictive maintenance to look at this, so you could bring in the gear manufacturer and the lubricant people who study the application, because otherwise they're just taking a guess of how to fix it.
Sure. Is there an industry best practice for determining oil change intervals on industrial gearboxes? And is there also a recommendation for how often the oil should be tested?
I have an opinion, but
No, go ahead. This is not an area I would be that good at.
Normally, I think the acid number and viscosity, drastic viscosity change are first of all, they are detrimental to the gearbox. So the idea is to see how much viscosity loss your gearbox can take, and it still can have the film strength to work. So the acid number, if the acid number is between 3 and 4, I would say again, it's time to change the oil. And the viscosity, if there's lost, its grade is, for example, it's 320 oil, 320 gearbox, and it has gone to 220 oil or 150 oil, you know that there is something, shearing is going on, or oxidation is taking place, or some contamination has caused it to accelerate the oxidation process. So all of this is important, but the two properties that are viscosity and acid number are critical.
Okay. Very good. Do we have any questions from the audience? All right, then. I'm out of reader questions. I would like to thank all of you for joining us today and learning about lubrication. I would especially like to thank all of our panelists for sharing in their expertise. And if anybody wants to learn more about any gear-related subject, you can go to geartechnology.com/TV and watch other episodes. Thanks for joining us.